Okay, so let's look at that. So we start with, okay, so this is the proof within the proof. So this is, I said proof before. Yeah, so this is the proof within the proof. So if f of G1 is equal to f of G2, now let's multiply this equation with the inverse of f of G1. So the inverse element of f of G1 is, we denote it by this. So we are multiplying both sides with the inverse of f of G1. And we are multiplying it from the left. So we have f of G1 on both sides. All right, so on the left-hand side, we will get E prime, right? Which is the element in G prime, the identity element in G prime. Okay, so on the right-hand side, we have f of G1 inverse acting on f of G2. But remember that f is a group homomorphism, right? And because f is a group homomorphism, that means that this should be equal to f of G1 inverse G2. Okay? So E prime is the identity element of G prime, and F maps this element of G into the identity element of G prime. So this is in G, and this is the identity of G prime. So that means that G1 prime, G1 inverse, G2 must be in the kernel of F, which we have written as K. Okay, so that means that G1 prime, G2 must be, so I want to keep on writing G1 prime. Sorry, my brain is not working today. This must be equal to some K for some small k, which is an element of the kernel. And in other words, what does this mean? If I multiply both sides, left multiply both sides by G1, we see that G2 is equal to G1 K, the small k. That means that G1 and G2 are coset equivalent. All right, so what we have shown is that if two elements are equal in over here, then their pre-image, well, under this map, well, they're not the pre-image because we're looking at the map from this thing to this thing. Then, they map to the same element in the coset space, okay? Is it clear? All right, so that was like proof that the map from the image of F to G over K is well defined. Now let's look at the opposite, the other thing, which is you have to show that the map from the quotient group or the coset space from G over K to the image of F is also well defined. In other words, we have to show that, well, it's actually very it's probably even easier. So let's show that. So another proof within proof is, so if G1 and G2 are coset equivalent, then G1 can be written as G2 times K, for some K in the kernel of F, then F of G1 because it's a group homomorphism, will take us to F of G2 of K, and well, because it's a group homomorphism, is when the assumption of group homomorphism comes in here, is that the right-hand side can be written as F of G2 times F of K. But F of K is E prime. So E prime times F of G2 is just F of G2, right? So we see that if G1 and G2, so if G1 and G2 are equivalent, that is, they belong to the same coset, then their images also belong to the same, they map onto the same image in the image of F. Okay, any questions? All right, so next, let's look at the group structure. So the group structure. So what do we have is that in G over K, and here we have image of F. On one side, we have stuff like G1K times G2K, right? And this multiplication, oh, sorry, this is not what I want to say. Yeah. This is what we have over, say, in G over K. And this gives rise to G1, G2K. And remember that this is the multiplication that we defined, and I think it was left as an exercise. So this is G over K. And on the other hand, in image over image of F, G, like this thing, maps to F of G1, right? Because this, whatever representative we take from this guy is just going to give you the identity there. And this thing similarly maps onto F over G2. And this thing maps onto F of G1, G2 according to our map. So we see that the map that we are constructing between these two spaces, you might call it big F or something, that map preserves the group structure, right? So this, we see that, thus we see that it's a one-to-one and onto map, and that it preserves the group structure, and therefore it's an isomorphism, okay? Okay, any questions, comments? You can always go over something again.
I didn't really get the last part. What was the point of this diagram?
Oh, yeah, sure. So, so we have two structures, right? We have a structure which is a coset space, which is a quotient group, right? And we have another structure which is the image of F, which is a subgroup of G prime, right? And according to the group homomorphism F, G of K1 maps to F of G1, right? And G2 of K maps to this thing, and this thing maps to this thing. But the group product here is the product in G over K. And the group product here is the product in image of F. So before this section, we were talking about, we showed that these maps between these elements was well defined. It's an invertible map, therefore it must be 1-to-1 and 1-to. What we are showing here is that, this group product, this group multiplication and this group multiplication, they preserve the structure, the binary structure, and therefore this map that we were talking about before is a group homomorphism, and because it's 1-to-1 and 1-to, it's an isomorphism.
I see. I think I get it.
Yeah, it's just like, because I didn't really talk about before when we, so suppose when we talked about the first map being well defined, we didn't talk about multiplication of these elements, right? And therefore it's important to show that the multiplication between those two elements, we know that gives rise to this element. That was how, the structure of this group came about. The quotient group is by definition, a group multiplication. We have to show that that group multiplication, that structure is preserved under this map, right? So let's make, comment or a couple of comments. Number one is that, geometrically, or I don't know if geometry is pictorially, is suppose on one side you have the group G, and you have elements in this group. Suppose these elements form the subgroup K, the kernel of F. And then, these elements form another coset, say G1 of K, so on and so forth. And on the other hand, say we have an image of G. Now, see that the first isomorphism theorem does not require F, the group homomorphism that we started with, to be an isomorphism. It can be, it doesn't have to be an isomorphism. So essentially on this side, all the elements of K are going to map to one element in the image of G prime. Sorry, image of, sorry, this should be image of F. Okay, right? So this kind of, all these guys get mapped into, smooshed into one thing under this map F. So this is F. So similarly, all these elements over here, that is all the whole coset, G1 of K, that gets mapped onto one element in G prime, the image of F, which is F of G1. So we see that this is basically, this map between, these subsets and these elements, that is an isomorphism. whereas the individual maps between the elements of G, and the elements of F, image of F, they are not isomorphisms, okay? Is that clear what I'm trying to say here?
Can you repeat the last part?
So yeah, we started with a group homomorphism F, right? And so this is all the elements in the group G, and these are elements in the group in the subset of G prime, which is the image of F, right? So see that map, which maps you from, it's a group homomorphism which maps you from G to G prime. Now that's not a one-to-one map. It's a many-to-one map. It may be a many-to-one map. It doesn't have to be, or it may be. So, but what is happening is that all the elements in one coset is being mapped to one element in the image of F. So all these, so we can think of this coset being mapped to this element in image of F. And this coset being mapped to this element in image of F, right? And this map, the map from the coset space to the elements of the image of F, that is the isomorphism that we are talking about in the first isomorphism theorem.